Hi, everyone. My name is Thomas, and I'm a student researcher at Columbia. And today I'm going to be talking about interpretable convolutional neural networks for infrastructure damage assessment after natural disasters using satellite imagery. So of course, like the motivation behind this work is that natural disasters are increasing in frequency and intensity due to climate change. Some of them obviously more than others. Extreme weather events particularly are the ones that are increasing in frequency and intensity. And this has motivated a lot of recent work in the past, like 5 to maybe 10 years on more like computational approaches to assessing the impact of these natural disasters. So that would be sort of the adaptation side, and then also like using those insights gained for mitigation purposes as well. So in terms of like the specific background, around like 60,000 people die a year from natural disasters. It also results in immense infrastructure damage, which is the aspect that we're focusing on in this work, and economic loss. And satellite imagery really is a great source of data to use because it is efficient, and like as time goes on, it's becoming more high resolution, readily available. And the sort of deployment idea of this work is sort of aiding in the allocation of resources. So it's like a triage mechanism where we could see which buildings were most damaged by the disaster, and then sort of allocating resources based on that. And we analyze this using deep learning-based approaches, specifically using convolutional neural networks because they're most suited for image tasks. So previous work in this area kind of like a while ago, like broadly focuses on like image classification. So like from classical approaches to deep learning techniques, and then computer vision for satellite imagery has been used for like so many purposes. And some of them have been like discussed. So like marine ecology, weather forecasting, spread of disease, urban road damage, agriculture assessment. And then one thing that is really relevant to our work here is like change detection. So if we have a set of data from a certain time frame, and then we also have data from the same locations, maybe like a day later, or in this case, like after a particular natural disaster, then that information can be relevant in terms of the actual input of the model. That could be like the pre-disaster and post-disaster image concatenated, or somehow like incorporating both of that into our analysis. Another way that this has been approached in the past is like training a separate model on the pre-disaster image and the post-disaster image, and then using the features gained from that to have another model and then have our prediction after that. But specifically in this area of building damage assessment, in the past, there's been work on like semantic building segmentation. So here on the right, you could see like an example of a binary classification task where the red buildings are not damaged, and the green one, or sorry, the red ones are damaged and the green ones are not damaged, and like the threshold for that could be like set at a certain level. So that's like a binary task, and then there's also like cross-region transfer learning. So in the past, a lot of data sets were not really global, and they focused on specifically for like change detection, they focused on like one disaster or something, and then like different works have used the insights gained from one disaster and transfer learning to gain insights from like another disaster that is like unseen data. And then there's also been like semi-supervised approaches where the data isn't necessarily labeled, or not all of it is. And then what we work with in this work, which is ongoing, is XBD, which is sort of the most comprehensive data set to date that like includes pre-disaster imagery and post-disaster imagery across a wide range of geographical locations, and also includes like an ordinal scale for classifying each building. And I will go into that like more in detail. And then another area of work that I've been working on that I won't discuss today because of like time constraints is like social media data, sort of like which can involve natural language processing and computer vision, because you might have imagery and text data in that for disaster relief as well. But what we focus on, and as I mentioned, is interpretability in both a quantitative and qualitative sense, and I'll get into what exactly that means. Instead of focusing on just the accuracy of the models and, of course, creating the state of the art, which is very important. It's also really important to see if we actually understand how the model comes to its predictions, not just having input data, receiving output predictions, and taking that for granted. So interpretability, the exact definition is quite simple. It's just the degree to which a human can understand the cause of a decision of a machine learning algorithm. Interpretability is important, especially for end users, because it allows society as a whole to sort of like trust the results of the model. It also enables us to uncover any potential biases in the results, whether that is as a result of the bias within the data or algorithmic bias. And so there are many ways that interpretability can be tackled. Some examples are activation maximization. So like understanding what each neuron contributes and what its purpose is within the grand scheme of the neural network. Attention visualization, layer-wise like relevance propagation, and saliency maps. And then a more simple way to do this, which is what we do here, or two ways, are saliency maps, which is like heat maps to understand like which part of the image contributed most of the prediction in that particular case, as well as like doing an analysis of different like input modalities. So when we input like more types of data or more like points of data, does that improve the results? So the process that we took was first some like pre-processing of the data and then developing a baseline model to classify building damage based on the post-disaster image only. So seeing like if we just have the results afterwards and not where the building started, does that yield any interesting information? And then to develop improvements to the baseline model by classifying building damage based on other aspects of the image, like pre-disaster image and disaster type, and then also experimenting with different loss functions, and finally looking at like qualitative interpretability in the form of saliency maps, and then comparing the results. So just a more in-depth background about the XBD dataset. So here is an example of like what one pair of images would actually look like. So you could see like a community before some type of disaster and then afterwards. And in this case, it was like obviously quite severe. In terms of the joint damage scale, which this data set utilizes, it ranges from 0, no damage, to 3, destroyed, and it's like on an ordinal scale from no damage, minor damage, major damage, destroyed, and those are like some descriptions of what that means. And then the great thing about this data set is that it is very wide in geographical range. So pre-processing, we took a number of steps. First, creating like building crops for each image. So instead of doing like semantic segmentation, we're actually just looking at each image scaled to the same size, or sorry, each building scaled to the same size. And we discarded like small and unclear buildings. We sort of like balanced the data set because there was a large number of like negative examples of buildings that had no damage. But in any case, the baseline model, we trained this on the post-disaster image only. We used a residual neural network with 18 layers, pre-trained on ImageNet data. So we use like transfer learning in a way. And then this is like the exact architecture of the model. So we had like a few like convolutional layers and then average pooling, fully connected layer, and softmax at the end. And then we use cross-entropy loss for this baseline model, which is pretty standard. And we trained on 128,000 building crops. That's like a typo. It should be 128,000. Using an Atom optimizer with a learning rate of 0.001, training for 100 epochs, using NVIDIA Tesla K80 GPUs. So that is the baseline model. And then the improvements that we applied were the new types of inputs, so the pre-disaster image and then the disaster type. And then also, finally, I didn't include the results in these slides, but the ground truth of the neighboring buildings. So obviously, if you have a set of buildings and around like one building, a lot of those buildings are destroyed, it might be correlated that that building in the middle is also destroyed. There's probably some correlation there. So that's another type of input that we also included. And what that would look like in like a real-time scenario is that like if we look at a certain number of buildings and like we have a very high confidence level for like the category of one building, we could use that as like a proxy ground truth for the other ones. Different different loss functions, we also experimented with our ordinal cross-entropy loss. So that is adjusting cross-entropy loss by including an ordinal scale, penalizing for the distance between the ground truth and the prediction. So if I have a ground truth of 3, but my prediction was 0, that's a lot worse than my ground truth being 3 and my prediction being 2. And then we also just like add like mean squared error in there to experiment. And sort of our results in terms of comparison are as follows. The pre-disaster image, post-disaster image, and disaster type as a model input perform the best with the loss function, ordinal constant entropy loss, within these 9 models. When we also incorporate the ground truth of the neighboring buildings, like I mentioned, and we also use ordinal constant entropy loss, that accuracy increases to around 85%. So that's not too surprising, and it's like good to see that when we add more modalities of data and use a loss function that is quite well suited to this task, we have higher accuracy. And in terms of our analysis of this, the reason for non-optimal accuracy in some cases, like we saw, like in the out of those 9 models, the highest was like 75%, is that this data set is interesting because the ordinal scale, which includes minor damage and major damage, actually resulted in somewhat of a low recall because like major damage instances were often classified as minor damage or vice versa, and the boundary between these two classifications are not necessarily like that clear. And this is like acknowledged in like the data set paper itself that was released. And so like a lot of times like images between these damage classes have minute visual differences, and there was like high confusion between these two classes. And if you look at like the F1 score for each of the each of the categories, it was higher for like damaged and not damaged at all. And then ordinal cross-entropy loss makes sense because we do have an ordinal scale. It's not like a cat versus dog. It's like a scale, and that means that was the best criterion for optimization. Next, we look at sort of like saliency maps. So what this shows using gradient-weighted class activation maps, or GradCam, is when we have a post-disaster image, which part of that image most contributed to the prediction in that case. So like from a intuitive perspective, what this could mean is that if we have a destroyed building and the prediction was destroyed, it might highlight in like more red colors the areas that showed evidence of like paint peeling off or like something that indicated destruction. And this is actually a form of interpretability that can be useful for actual like deployment and end users, because in the scheme of allocation of resources, it might be useful to see like within even a building, if it's like large, for example, where should we like triage resources, even like within like a smaller scope, that could lead to effective disaster relief. And then so our broader conclusion, before we get into like what we're working on now and like future work, is that inputting different combinations of information does indeed improve model performance. This is important for like effective damage assessment and trustworthy damage assessment in the event of a disaster. And as climate change increases the frequency and intensity of these extreme weather events, it's increasingly important that these are accurate and interpretable. So future work, I already mentioned like neighboring buildings and using the ground truth. Another idea, and this has been like previously implemented in some ways in the literature, is using like different combination methods for the pre-disaster image and post-disaster image. So what we did is sort of just like concatenate them over the RGB channels and use that as an input, and then for like the disaster type, like one hot encoding that like between like the set of like 7 or 8 like different disasters. But another method would be to train like here, like one ResNet 50 on the pre-images, one ResNet 50 on the post images using shared weights, and then taking the features that were gained from that into like a semantic segmenter, like damage regressor, and then have that like final output. And And then another aspect would be like deployment of these like qualitative interpretability, and then also exploring interpretability in different ways. One idea that I mentioned was that we're currently working on is activation maximization. So seeing like which neurons and which layers contribute like which aspects that lead to the prediction. And then other ideas like attention visualization and layer-wise like propagation. And then another aspect would be like more data sets that are similar to the XPD, but maybe have better like labeling mechanisms, more distinct differences between major damage or minor damage, if we want to do like a non-binary classification like this case, or something like that. So like data is like very important. So like pre-processing and then different interpretability techniques, and then adding like potentially other modalities of input are kind of like the current direction of this ongoing work. And that is the end of my talk. We have about a couple minutes for questions, so.